Hello and welcome to Unprofessional Engineering. My name is James.
And you got Luke.
Luke, how do fiber optics work?
I'm assuming black magic, maybe a little bit of interdimensional space travel.
I was going to say aliens have to factor in.
Without a doubt, aliens are involved. Interestingly, James, that is not true. We were just kidding. It's not black magic and aliens. There's actually science behind it. Or did you just do black magic and alien communication technology?
That's literally all I have written down in front of me. So
show's over.
I guess you are in charge. Luke,
No. We
need to talk about the history.
We do, because I know you love your histories.
I love history.
The earliest I have is 1970 or 1790. If you have something
I was
going to
say, my goodness.
You know me and my dyslexia. Sorry.
I know. 1790 sounds like a great place to start.
No. We're going to start there. Okay.
So 1790s? Yeah,
1790s. So optical communication systems date all the way back to the 1790s.
That's what I gathered.
This thing was called an optical semaphore telegraph. I think I'm pronouncing it.
I think you nailed it.
Semaphore. And it was invented by this cat named Claude Chappé. He's French, so I had to put the A on the end of it. And this was during the French Civil War. There's always a war tie-in.
There is always a war tie-in.
And the problem he was solving, so this is not a physical fiber optic cable, folks, the way that you're thinking of fiber optic cable, which is what our main topic is today. But this is optical communication. So imagine, James, a windmill.
I'm imagining that.
And on top of this windmill, there's this big old post that sticks up. And then there's there's a 3-bar linkage. So 1 in the center and 2 on either end.
3 bars.
Yeah, 3 bars.
Linked.
So what Claude did was he devised basically a visual representation of letters and or words that as long as you could see the line of sight from one windmill or tower from another tower, you could communicate literally hundreds of miles in minutes rather than months, because during the French Civil War, apparently getting communications back and forth was as fast as a horse could ride. So a part of it was making sure that you could communicate effectively, and it was essentially kind of like Morse code, but it was this little
That's
visual.
What I was thinking.
There's like a map of what each thing means, and they would just send a message, and they said they could send a message. I forget how many kilometers. It was like 100 kilometers or something like that in like 10 minutes.
Wow.
That's all.
Just because you'd go from one tower to the next, to the next, to the
next. Would repeat. So the first tower would start the message and would continue, and from one to the next. It was very similar to lighting the fires of Gondor.
That's exactly what I was thinking about.
Exact same thing.
Yeah, makes sense to me. So you covered a lot of stuff right there, and it brought up a lot of questions and topics for me. First, if you haven't checked out our episode on windmills or windmills versus wind turbines, go do that.
Yes.
Second, what do you think a civil war in France is like? Like both sides are just surrendering, and whoever surrenders the most loses, or like, well, how does that work?
There goes our entire French audience.
Yeah. Okay, moving on in history.
What
else do you got?
The next thing I got is actually kind of getting into more fiber optics, like as real
so the next thing
this is 1840.
Oh, go ahead. Yeah, no, you're right in line.
So the concept of light transmission. So keep in mind, optical communication was just visually seeing it, but this is actually transmitting light. So bouncing light, essentially, was around as early as 1840, when French inventors Daniel Colladon and Jacques Binet demonstrated that they could guide light over distances.
I don't think it's just Jacques. Is it Jacques? I don't know. I don't have it written down. I'm just wondering.
I have no idea. You know me. I'm not the resident lexicon.
That's true.
But they could guide light over long distances through refraction. So basically mirrors, or they used water in some cases to refract the light back and forth. And that was probably the earliest where it was actually light being transmitted, similar to what's happening in today's fiber optic cables.
That's interesting. So I saw that our buddy, like good friend Alexander Graham Bell
Good old
also
bellies.
patented
Yeah.
an optical telephone system called the photophone in 1880. So that also tied in. That same year, William Willie Wheeler invented, I wonder if people think that his name was Willie. Anyways, William Wheeler invented a system of light pipes lined with really reflective coating that like illuminated homes. And by using that light from an electrical arc lamp, like the real old, what I think were dangerous arc lamps, placed in the basement and directing the light all around the house with these fancy reflective coated pipes. So that's kind of neat. If you haven't checked out our episode on Alexander Graham Bell, I think you should do that one because it was very interesting and you'll find out that he's basically just a thief. So good job, Alexander Graham Bell. That's where I ended my history lesson. Do you have more?
I got a little bit. So in we're going to jump all the way to 1952.
All right.
So in 1952, a UK-based physicist by the name of Nadir Singh Kapai invented the first actual fiber optic cable that actually works the way we think of fiber optic cables today.
Boy, that's so long ago.
He based the design of the cable on John Tyndall's experiments 3 decades earlier. So 30 years earlier, the idea of doing this was developed, and this guy actually built the first one. And it took all the way until 1965, 13 years after Nadir, British scientists Charles Kao and George Hockman, working with standard telephone and cables, discovered that attenuation in fibers, attenuation is loss of signal, essentially, was caused by impurities in the manufacturing process. So they were wondering why, like, over long distances, the signal would get degraded and not work or wasn't as fast. And it was all basically the quality of the material and basically the clarity of the glass. I don't want to give it away. There's glass in the middle of these things.
You did really just give it away.
Sorry.
Well, let's call it an episode.
And the last piece of history I have is 1970. Do you have anything?
No, you're good.
So the attenuation barrier was broken in 1970. So this is 5 years before my glorious birth by 4 research scientists working at none other than Corning Glassworks.
Makes sense.
Robert Mauer, Donald Kneck, Peter Schultz, and Frank Zimmer. And essentially what it came down to was, like Corning does, they just do all kinds of things amazing with glass. They made the most pure glass with the lowest attenuation loss. And it was all because of the way they manufactured and what the process was and how they monitored the manufacturing process of the actual glass fibers that are in fiber optic cables.
And if you haven't, for some reason, checked out our Companies That Built the World Corning episode, you would find out that they were one of the first R&D labs in the United States. So it only makes sense that the R&D glass place would be the one that would come up with this sort of stuff.
That was one of my more favorite Companies That Built the World. They were pretty interesting.
They were very interesting.
So that's it with history that I have.
I love it. That was a great history. So what I want to cover next is kind of like, what is fiber optic cable? But before we do that, we should probably take a break for a word from our sponsor.
And none other than Corning.
You know, it feels like it should be.
We're not allowed to say that, are we?
You are going to get us sued. We do have a couple shout outs. Yeah. Amos M., one of our listeners from down under, 13 years old, wants to be a mechanical engineer.
Way to go.
Cars and robotic arms with his Legos. So like way outside my league, right? And most importantly, has listened to all episodes at least 3 times as he drifts off to sleep.
So Amos, I think if you didn't hear it already, talk to your parents about buying old electronics, take them apart, put them together. It's one of the best things you can do as a young engineer is learning how to take things apart and put them back together. Sounds like you're doing some of that, but if you're not already taking old VCRs and things like that apart without them plugged in, they can't be plugged in. You got to make sure they're not plugged in. Safety first.
Don't take an old VCR apart. It's probably worth a lot of money because nobody has them. Another shout out, Andrew C., a mechanical engineering student at Cleveland State University.
Mud Ducks. Way to go.
Not going to hold it against him, even though we're not real happy with Cleveland these days.
Jerks.
Yeah, he is starting on his 2nd time through listening to our episodes. Like, We have some great fans out there.
We
I
do.
love it.
We do.
Wanted to share a cool story with us. A
Shoot.
man with Parkinson's disease posted a video on social media, TikTok, complaining about how difficult it is to open up pill bottles, right? Another TikTok user took him up on this or took it upon himself to design a CAD model for a better designed pill bottle and challenged other users with 3D printers to help create, design, and improve on this pill bottle. This all started only about a month ago, and there are now 5 different versions or more of this pill bottle. And the original designer is working on with a patent lawyer to make the design free for anyone who could benefit from it
How nice
for
is that
their
that he
medical
made it
conditions.
free?
That's
awesome.
super nice. But he just wanted to share that cool story. If I am correct, I think they used Fusion 360 to design.
The original. I saw the videos and all the stuff happening with that. The original video and the design of it was done using Fusion 360.
So cool. Andrew, thank you for sharing that. Really nice story. And let me tell you what, TikTok is not high on my to-do list of things, but good for you. Like, good for them having that kind of content out there and not just dancing people. So if any of you have awesome stories like that, if any of you are listening to our episodes for the 4th time through, or if you just want to say hi, get some sweet stickers, or whatever the case may be, why don't you email us at unprofessionalengineering@gmail.com.
And don't forget to subscribe, to like, to share, give us reviews and ratings. We'd love to hear from that. And as always, you can tell your smart devices to play the Unprofessional Engineering Podcast.
Fiber optics, Luke, or optical fibers, if you want to be that guy, are really long, really thin, pure glass, just like you were talking about. You ruined it for everyone, but that's okay. We won't hold it against you. Really pure glass, about as thick as a human hair. Not
a little thinner, actually.
A little
in some
thinner.
cases.
Well, I said about. What do you want me to say? Come on. And they're like all bundled up, right? So it's not just one little hair running through stuff. It's a whole bundle of little hairs that are combined together to form an optical cable. And this is used to transmit light signals over super, super long distances. And so these are made up of 3 main parts. There's the core, the cladding, and then the coating. The core is just that thin glass center that the light travels through. Pew, I assume is about what it sounds like.
Exactly what it sounds like.
Cladding is the outer optical material that surrounds that core. It reflects the light back into the core. Like if it's trying to get out, it's like, no, get back in there. Boom. That's the noise it makes. And then there's the buffer coating. And so that's like the plastic coating that protects the other parts. It keeps moisture away. It keeps me from cutting it and causing problems, all sorts of stuff like that. Hundreds or thousands even of like these optical fibers are arranged in these bundles, and the bundles are protected by the covering, which is called a jacket. If you're in the business I am.
If you're in the business, I think it's called the plentum, actually, is maybe the right word.
That's fancier than I am. There's 2 different types though, Luke. Do you know the 2 different types?
I'm fairly certain one of them is called a single mode fiber.
Ooh, very good.
And the single mode fiber is a very thin. It's about 5 to 10 microns. That is 1/1,000,000th of a meter for anybody that understands what that even means. Like, why would you even put that in the like? Why would I say that? That's dumb to say. What's a millionth of a meter?
Before I didn't know, but now I'm for sure.
Now I know
what that size is. Yes.
And in a single mode fiber, all the signal travels straight down the middle of that fiber without bouncing off of the edges.
Wow.
And the reason why this one is used for really long distance travel is because it's literally like instantaneous. I mean, you can measure it in like seconds how long it takes to get there, but like whenever you hit, theoretically, if you hit send, it's practically instantaneously on the other side of the world.
So crazy.
All the different switches and software and all that sort of stuff kind of get in the way and slow, emails and all that sort of stuff down. But the reality is, theoretically, I'm pretty sure that it can do 1 petabyte per second over 50 kilometers. I don't even know what a petabyte is.
I feel like you're just saying words that I've never heard before.
So PETA, 1 petabyte per second. It's bigger than a terabyte because a terabyte's after a gigabyte. I imagine that's probably 1,000,000 gigabytes or 1,000, whatever. It's a lot. So
It's 1/1,000,000th of a meter. That's all.
why did I say that? I'm sorry.
I love it.
And then the other one is multimode, which I'm sure you know a lot about.
I don't know much about it, Luke, but I know that it has massive cores. Like the other one we're saying was like really, really small. This one's massive because it's 62.5 microns in diameter, give or take.
It's 10 times bigger.
Yeah, it's massive. So the single mode that you were talking about, it uses infrared laser light. That laser,
Pew, pew, pew.
nice. So wavelengths around 1300 to 1550 nanometers. And then for the multi-mode fibers, it uses infrared light as its preferred method with light wavelengths in the 850 to 1300 nanometers area. And this is all emitting from LED lights. So
interesting thing
diodes
about the multi-mode is multi-mode, it actually bounces through the glass. So instead of like going like straight down the center,
which is also why it's not necessarily used for the super long range.
Long distance. Right? They said it's typically like local area networks. So like a data center would use it to connect computers all together. They would use that type of fiber optic cable, where if you were doing a transatlantic cable, let's say, you would use a single mode because it would take way too long to get there.
Okay. Fun fact for you, Luke.
Shoot.
I know we said that these are all made out of glass and it ruined everything, but some can actually be made out of plastic. And these fibers have actually, relatively speaking, very large cores, which would be like a 1 millimeter diameter core. So still very small, but comparatively speaking, very large. And these transmit visible red light at a wavelength of about 650 nanometers for anyone who's
I got a fun fact for you.
You are always so fun, and I need to hear it right now.
It was originally developed for endoscopes in the 1950s.
Oh,
and the idea was doctors wanted to see into the human body without having to cut you open first.
I appreciate that.
In the 1960s, so this is before that 1970 timeframe I talked about previously, telephone engineers thought, hey, we could maybe use this for, speeding up telephone calls, and they kind of started to adapt that technology. And then that's where that 1970 timeframe came from, where the very first cable was designed.
Very interesting.
You ready for another fun fact?
Always.
So, so this is less than a tenth as thick as a human hair and can carry something to the magnitude of 25,000 telephone calls on a single fiber optic cable, and can easily carry several million calls. So
my goodness,
that would be enough roughly for 1 million Zoom sessions to occur. That's per second, because it's 778 terabits, a trillion bits.
That feels like that would cover about half of one of my days of Zoom calls at this point. So that's very useful.
Yeah.
That's crazy, isn't it?
Like these numbers, so I get mad. No, they don't. Like I get mad whenever like Cobra Kai is buffering whenever I'm trying to watch, or whatever I'm binging.
Somebody terribly spoiled.
I'm gonna give my own shout out. The show on Netflix, Somebody Feed Phil, is amazing. If you haven't seen it,
never heard of it.
It's really, really good. If you like food and travel shows, the writer is the guy that Everybody Loves Raymond. He's hilarious.
Oh, nice.
And he's the star of it. So, but yeah, it's just crazy. Like I complain about like the fact that I got to wait for things to download, and then I hear this stuff is out there.
Yeah. Do you remember dial-up? Oh man, good times.
Sorry.
I love that noise. Okay, before we move on with any more about fiber optics or optical fibers, I think it's time for this week's Luke's Rant.
So this is more of like a question for our listeners. So for the last, I'm going to say 7 years since we've been in our current home, I've been arguing, fighting almost with my wife about the home phone, like the landline in the house. So we've had one now in the house for 7 years, and my wife refuses to get rid of it. It only costs us like $7 a month. It's super cheap, but it's the whole point of I'm paying for something that I never, ever, 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 ever use. And I'm wondering how many people have landlines in their house, or they exclusively are using, either something online or they're using a cell phone 100%. So James, where are you at with this? And then I'd love to hear from our listeners where they're at.
I used to have one technically in my old house. So up until a year and a half ago, we'll say, I didn't actually have a physical phone in the house. I just had a number tied to my name so that I could get the bundle deal of cable package phone because that was cheaper through the cable company. Now I no longer even have that phone number associated to me, just my cell phone.
So I have in my basement, there's a phone on the wall that looks like if you hold it too close to you, it's going to like give you cancer kind of phone. Yeah. It has a little coiled thing coming off of it.
Oh, that's so great.
It's literally, the phone is probably 30 years old is my guess.
Yeah.
And that's the phone in the house.
Does it ring?
It does ring. So whenever telemarketers call, I can hear it ringing in the basement, but it's just crazy. I don't know why we have it. And I just wonder how many people do. Maybe I'll have some ammunition the next time me and my wife have this discussion.
There you go. That would be very helpful. All right, Luke, moving back on to the optical fibers. Do you know how it works?
How it works?
Yeah, how it works.
I got a little bit of how it works.
Well, let's hear about it.
Didn't we just do how it works?
Well, I just wanted to go a little bit more into it. But
you
that's
can dig
okay
into that.
I'll
do how it's made. I was more interested in how it's made.
Let me see if I even have that. I don't even have how it's made. Why did I miss that one? Okay, real quick on how it works. So I saw an analogy on one of the many pages I looked at and didn't steal from. It was saying, like, imagine shining a flashlight down a hallway, right? And then you're going to bounce it off of mirrors so that if there's a bend in that hallway, the light goes along with it.
Mm-hmm.
If it's a straight hallway, super easy, right?
Yep,
it shines down there.
Speed of light.
And then eventually it kind of fades, the signal becomes weaker, and you can't see light further down. If there's a bend, it has to use a mirror to bend. And the same thing happens though. So even though we're able to shine these lights, and the same thing with fiber optics, we also still need like boosters along the way. So they're called like optical regenerators, I believe. And it's kind of like if you have Wi-Fi in your house, but you have a room that's too far away, you need like a Wi-Fi booster. I kind of imagine it being the same sort of thing there. So the light in fiber optic cables travels through the core, which would be the hallway in this case, by constantly bouncing off of the cladding or the mirror lined walls. And again, this is in the multi-core, right, that we were talking about. And this principle is called total internal reflection. Because the cladding does not absorb any of the light from the core, the light waves can travel super, super, super big distances. So I'm not convinced this is a fun fact, but I'm going to say it anyways. Total internal reflection in physics is the complete reflection of a ray of light within a medium, such as water or glass in this case, from the surrounding surfaces back into the medium. This phenomenon occurs if the angle of incidence is greater than a certain limiting angle called the critical angle. So did that clear things up for you?
I mean, it was, of course, the critical angle.
I know you didn't need that explained to you, but I thought maybe some of our listeners might be like, well, what the heck's total internal reflection? So some of the light degrades within the fiber, mostly due to, like you said, the impurities of the glass. We haven't perfected this process just yet, and it's super expensive. The extent that the signal degrades depends on the purity of the glass and the wavelength transmitted. So there's four main parts. There's the transmitter, which produces the light signals, and it kind of acts as an on or off switch, like a light switch off and on. It's kind of like that. There's the optical fibers, which we've talked about all this time. The regenerator, which I just mentioned, which is like your Wi-Fi booster. And then the optical receiver. And the receiver receives and decodes those light signals. So it takes that incoming digital signal and it turns it into like the electrical signal that other devices use, like your telephone or your computer or your TV or whatever the case may be. It then turns it into those. And the receivers use photocells to detect that light.
And if you don't have a receiver, what you end up with is one of those little desktop lamps that have the spaghetti sticking out of it and the little lights come out of the top.
Yes, and they're very pretty.
If you put a receiver on the end of them, you'd understand what that light meant.
Well, there you go. Luke, how's it made?
Okay, so I hate bringing this. Should have just been a Corning episode. The number one supplier of fiber optic cables in the world is none other than New York-based Corning. They have been this leader since they invented that back in the 70s, the low loss optical fibers. They have 16.3% of the market share for producing and selling fiber optic cables worldwide, which
That seems pretty good.
it's dramatic. I think the next closest competitor somewhere in the single digit percent wise. So clearly the market leader.
How are they
So
not sponsoring us?
Someone's got to be listening at Corning. Come on now.
Yeah.
So here's how it's made. There's this box where black magic happened. No,
Is this the bread box again from the last episode?
No. So it starts with what's called outside vapor deposition, or OVD. Do you want to talk about OVD since you know about OVD?
Yeah, you know me. No, I do not want to.
Okay, so OVD, or outside vapor deposition. So imagine there's this chamber, right? And there is a rod inside of this chamber. What they do is they deposit the raw materials as vapor onto this rod. It's basically, a substrate to take all the raw materials necessary to make, I'm going to call like the blank that they're going to make. So super, super critical. There's all these, and it was a really long process to develop this, but now it's so refined. It's super, easy to do. It's all, computer
super
controlled.
Easy.
I'm not going to say super easy. I mean, once it's done,
you just did.
So once these happen, what you end up with is you have this. It looks like a blank. They called it a preform. So imagine like, you ever seen how they make like Pepsi bottles, the plastic Pepsi bottles? It's a little piece of plastic like this, and then all of a sudden they turn it into something else. Same kind of thing. So there's this preform, and it's porous and it's not clear, and it's probably I think it's like, it looks like a charcoal color. Then what they do is they take this preform and they bake it, and that's when all the magic happens, and it turns into a transparent solid that is so pure that the contaminants in it are measured in parts per billion.
Wow. With a B.
With a B, billion.
Wow.
So now you have essentially this glass slug, I'll call it. After that has been done, the different size glass slug is then drawn into individual threads. So based off of how big the slug is going to determine how big the individual piece of fiber optics can be. And Corning has developed all kinds of ways to make that longer and longer and longer. So the draw process, it's really similar to, we did the thing on Gorilla Glass the one.
I was just going to say that. Yep. That was also the Corning episode.
Yeah. Apparently there's this thing about just drawing glass that just refines it and makes, just changes the properties of it. So imagine they put this slug really high up. They heat the tip of it, and then as that first blob, just the very tip of it, and then they keep it warm. And then as that blob falls, and we've all done this with like peanut butter or honey, a really thin piece forms behind that blob. There's probably some physical, phenomenon that's occurring there that I can't remember the name of.
Sure.
And then you have this super thin piece of glass that they monitor the speed, the temperature, everything of to make these individual pieces in the draw process. So once they draw that, then the coating is added. And then after the coating is added, then that final jacket is put on the outside of it. And shoot.
Well, my question when I was thinking about it is like, well, then how do you ensure the thickness and everything? But they have everything so like temperature controlled and weight controlled that it just kind of forms in that way then. Is that right?
Yep.
Wow.
They're constantly adjusting that temperature at that, I'll say the outlet whenever it's starting to draw to maintain. And it's so monitored. They said something like, there's literally hundreds of measurements per second to ensure the quality, because if there's one, it's a pipe. So if one portion of that pipe is bad, stuff is going to get clogged. So you have to make sure that these pieces of fiber optics are perfectly pure all the way through. And that's what the low attenuation, that loss of signal is what Corning is really good at. So then they bundle these up, and it's glass, but somehow it's flexible. Again, has to do with the mechanical properties. They can roll it into bundles and it doesn't break. Like if I have a piece of glass and I bend it, it's going to shatter. But so then they roll it up and then they ship it all over the world.
They do a bunch of testing on it too.
Boatloads of
But
testing. Boatloads.
that's kind of boring, so we don't really need to talk about that. But yeah, that's crazy. That the process has to be amazing to see, right?
Yeah.
Or just the things that go into it. I have a couple of advantages of fiber optics, Luke. Do you want to hear
Shoot.
them? Less expensive. It's a good one, right? Several miles of optical cables can be made cheaper than the equivalent length of like a copper wire, which people would then steal out of your walls or the ground anyways. It's a lot thinner, so optical fibers can be drawn through like smaller diameters than a typical wire could. It has, as you've mentioned, much higher carrying capacity for all of your needs. There's significantly less signal degradation from like a copper wire. It uses light signals. So, unlike electrical signals in a copper wire, light signals from one fiber do not interfere with those from a fiber in the same cable. So, less interference. It means like you'll have clearer phone conversations, you have better TV reception, better internet service, all of those things because of lack of interference. It doesn't use a whole lot of power. Fiber optics degrade less digital signals. So, optical fibers are really well suited for carrying digital information, especially for computer networks, as we've mentioned. This is a good one that I never would have even thought of. They're non-flammable. Since there's no electricity passing through them, they're using light signals. They're not a fire hazard, unlike wires that sometimes cause that, especially in older houses. And super lightweight. They weigh way less than the equivalent of copper would weigh. So
One
take up a
drawback that
lot
I
less
know
space.
of, personally,
Oh,
is
really?
yeah. So apparently, fixing a piece of fiber optic cable is far more difficult. You need some pretty specialized equipment because you're actually, I don't know if it's called a fusion welder, where it takes, so
Okay.
imagine you broke a piece. So I had this happen at my old house where our Fios coming in, which is fiber optic, the cable broke because someone was cutting down a tree and the branch hit it.
That'll happen.
That someone was me. I was not going to admit that, but
I wasn't even going to ask. You could
so
have
I was
gotten
like,
away.
"Oh, how can I fix this?" And then apparently, you have to have very specialized these tools that fuse the glass back together. Where if it was a typical cable connection with that solid wire in the center, you just cut it and put
Twist
a
those
little
suckers,
twisty
yeah.
thing on, and you're done.
Yeah.
So a lot more difficult to fix. But I do have a couple fun facts before we wrap up. If you want to hear them about,
I need some fun in my life.
So there are over 250 active underwater fiber optic cables that look like a spider web. If you saw a picture of the fiber optic cables on the sea floor,
Okay.
it's just everywhere. Tons of stuff going to New York, tons of stuff going to California where they all converge, over in India and Spain and the west coast of Africa, just tons and tons of it's amazing. 443 total cables are there, only 250 are active, and that's equivalent of 621,000 miles of fiber optic cables on the ocean floor.
Do you know why only some are active?
They're still in the middle process of laying them. It's a super long, difficult process.
I didn't know if it was like, now these ones are broken or
no,
something.
And like companies own them. Like Google owns some of these, and they lay them themselves. So I watched a video how they do it. I think one of our episodes is going to be about laying fiber optic cables on the seafloor. It was amazing.
People have asked for that before.
Yeah,
actually,
it's pretty cool.
Interesting. That's great. Anything else?
No, that's all I got.
Awesome. Well, if any of you have any questions about fiber optics, I would Google that. But you could also email us at unprofessionalengineering@gmail.com. And until next time,
see ya.